Our next example from 3.9 is number 27 in your book. Gravel is being dumped from a conveyor belt at a rate of 30 feet cubed per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? Okay, lots of information here. I already started the picture that it says we have a conical pile, so it's cone-shaped, and we have a associated height and diameter of that cone. Alright, so your find and your given, known, is what you should work on first. For the find, let's see what we have. How fast is the height of the pile increasing? And so how fast is indicating a rate. The height is what the rate is of, or how fast that height is changing. So all that translates into dH over dt. And then we're supposed to do this specifically when the pile is 10 feet high. So this is when h equals 10 feet. So now let's work on the given and the known. And so we have that 30, and that has the units of feet cubed per minute, which give us a hint that this rate that's given is dV over dt, change in volume with time. Some other things, a little bit in disguise here, but it says the shape of the cone whose base diameter and height are always equal. So we need to note that at some point, whether it be here or later. A little bit later is okay, but that's not always true that the base diameter and the height are going to be equal. It's a special thing for the situation. So I just need to note that somewhere along the way here in the beginning that d is equal to h. Okay, I think we're ready to move on to the equations that relate what we have. So what I would suggest is writing down the rates that you're trying to find, or that you know. That would be dV over dt. Take off the rate part, and the volume is something that has to be a part of at least one of our equations, okay? The other thing is what we're trying to find, dH over dt. And so we're going to introduce that derivative part. What we're trying to do right now is we're trying to figure out what's the equation that we're going to take the derivative of. And it's got to have an h in it. So those are the rates that are accounted for. We know dV over dt, so if that's produced after taking the derivative in our equation, we can account for it by plugging in 30. dH over dt is what we're trying to find, so the fact that that's unknown and is produced in our equation after taking the derivative is great. Now anything beyond that is not really accounted for, but we can handle with some other things. So V and H is what we need in an equation. So V is volume. That lends itself to the equation for volume of a cone. So that equation is V is equal to 1/3 pi r squared h. And this is an equation you're going to have to memorize, and I'll give you a list of that pretty soon. So here's our equation. Now let's go back and imagine our picture in motion and try to figure out what is changing with time. So the height is increasing. That's something that's going to happen. The diameter is also increasing, so it's getting bigger. Diameter is something that we don't even have in this equation, but note that the diameter and the radius are related, and so we can take care of that. Maybe we should do that right now. So that's the generic formula, but because we have a diameter in this formula, maybe the d equals h thing, and diameter is part of this. Let's just put this in terms of d. So then what we'd have is d is equal to 2r, and so solving for r, we get r is equal to d over 2. So let's plug that in. Take another look at it. 1/3 pi, and then we have d over 2 squared times h. Okay, so looking back at this, the diameter's changing, the height's changing, the volume's changing. But we only have rates accounted for with the v and the h, not the d. So here's where you need to say, I'm not ready to take the derivative of this, because when I take the derivative with something in here that changes with time and I don't have that rate, associated rate like dd over dt in this case, then there's something else some other relationship I need. So here's where you need to note that you're given that the base diameter is always equal to the height. So that's a constraint we can use to write what we have here entirely in terms of h. So we want to do that in the beginning. So we have 1/3 pi, and then we can just have this little equation for d equals h, and so now plug in the h for d. And now we have an equation where we have v and h in them, and those are the variables, and those are accounted for with rates, so that's great. Let's just simplify. So we're going to have h squared over 4 times h. Then we're going to have pi over 12 times h cubed. Now we're ready for the derivative step. So we want the rates, so that means that we need derivative with respect to time. So you don't have to write this stuff if you don't want to, but I always write it in for you guys so that you actually see that it's not the original equation that I'm handling here and writing down, or like with algebra or something, I'm taking the derivative now, that's what I'm doing. So now, the v is by itself, this is like example 1, we get dv over dt. On the right hand side, this is also similar to example 1 now at this stage. We had more work on the front end. We have a constant, pi over 12, and then the derivative of h cubed, where h implicitly depends on d. We're going to use a chain rule here where the h is the inner function. So, what that amounts to in this case is just taking the derivative with respect to h, and then multiplying by the derivative of h with respect to t. So the next and final step is to sub in and solve. So what do we have? Well, dv over dt is 30, it's accounted for. Pi, 12, 3, I guess I can simplify that. H, do we have that? When the height is 10, it's not a problem. And we're trying to find dh dt, so the fact that we don't know it is a good thing. So when we sub in, we get 30 equals, and pi over 4, so reduced to constant, and then we have times 10 squared, all that times dh over dt. So we just solved for dh over dt, and we'll call it a day. So dh over dt is equal to 30 and then let's see here, we have times 4 divided by 100. So you can write that exactly in reduced form, just as an aside, as 6 over 5 pi. But if you want, you can just write the approximate answer as 0.38. So just need the number part of the answer, but if you want to write the units, it would be feet per minute.